Hey there everyone, one more problem for today. This one is pretty short. We're going to take a textbook, which is represented by this green square here, and push it up against this spring by applying a force. This will compress the spring by 1/4 of a meter, then we will let the textbook go and launch it. It's going to slide across this tabletop and slow down in the process before eventually coming to a stop. And our job is to figure out how far it was displaced from the launch position by using the work energy theorem. Remember that the theorem states the net work done by forces on an object equals the change in kinetic energy. Let's simplify this a bit for our situation. When the book stops sliding, it comes to rest. Therefore, the final velocity is just 0. Additionally, before we launch the book and it's still touching the spring, there's no initial velocity either. That's 0 as well. So in this situation, the net work is purely 0. Let's think about what forces are doing work here. Some amount of that work has to be positive and some has to be negative, and they have to be equal to one another for this to be true. If the book is being launched, say, in the positive x direction, then it's reasonable to think that the positive work involves the spring and the negative work is done by friction. But here's the question. Is it the work done on the spring or by the spring? Just writing W with a subscript of spring is not specific enough. That's too vague. Here's a helpful reminder. If you are compressing a spring to the left with the positive x direction pointing to the right, then you are applying a negative kx force on that spring. If you integrate that to get work, you will end up with a negative quantity, and that will not fit our situation here. We need something that's positive to counteract friction. So instead, let's get the restoring force of the spring itself, which acts in the positive direction against our push. Notice that this force is just the negative of what we're applying on it. With the correct force identified, let's figure out what the work done by the spring would be in this situation. We'll need our generalized work definition that involves an integral that we covered in a previous video. Since there's only movement in one direction, we can drop this f vector for just kx, and we can switch out the infinitesimal displacement vector for just dx, like this. And we'll integrate that from the initial position of the book, which we can just call x is equal to 0, to the negative distance to which we compressed that spring. Integrating this is really simple. It's just 1/2 kx squared. And when we evaluate at the endpoints, here's what we get. The negative sign of that compression distance melts away because we end up squaring that quantity. So overall, the work done by the spring as it's being compressed is positive. So we're good. Let's go back to our sum of works equal to 0 equation. I'll plug in our result for the work done by the spring as well as the work done by friction. Since the work done by friction acts over the entirety of the displacement, we can bring this quantity over to the other side and then isolate d, the displacement variable, to finish the problem. After you plug in the numbers, don't forget to whittle your answer down to 2 significant figures. Here's the result. That's all for now, folks. Take care.